In 1917, the Pennsylvania Railroad built the most powerful electric locomotive in the world. It was longer than most steam engines, heavier than anything else running on American rails, and capable of hauling freight trains that normally required multiple locomotives working in tandem. The Pennsylvania Railroad designated it Class FF1. The crews who operated it called it Big Liz. Within 3 years, it became clear that the FF1 was fundamentally flawed. Not because its motors failed, not because it lacked power, but because its designers had overlooked a basic principle of railroad engineering, one that would make the locomotive increasingly dangerous the faster it ran. This is the story of Big Liz, the most extreme electric locomotive experiment of the early 20th century, and why the Pennsylvania Railroad never attempted anything like it again. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. To understand why the Pennsylvania Railroad built something as radical as the FF1, you need to understand the challenge they were facing in the mid-1910s. The Pennsylvania Railroad had committed to electrification earlier and more aggressively than any other American railroad. Beginning in 1910, they electrified the approaches to New York Penn Station and the tunnels leading into Manhattan. Steam locomotives were prohibited in these tunnels due to smoke and ventilation concerns, making electrification not just preferable, but mandatory. Early electrification proved remarkably successful for passenger service. Electric locomotives provided instant torque, required no time to build steam pressure, and eliminated smoke entirely. The PRR's initial electric passenger locomotives, particularly the DD1 class, handled commuter and passenger trains efficiently. But freight was a different matter entirely. Freight trains were heavier, slower, and required sustained tractive effort over long distances and steep grades. The electric locomotives that worked well for passenger service were inadequate for heavy freight. Moving a long, heavy freight train over the grades of the PRR's main line required enormous continuous pulling power, far more than any single electric locomotive of the era could provide. The standard solution was to use multiple locomotives, but multiple locomotives meant multiple crews, increased operational complexity, and higher labor costs. More importantly, it meant coordinating the operation of several machines, each with its own characteristics and limitations. The Pennsylvania Railroad's engineering philosophy at this time favored bold, centralized solutions. If a problem required power, PRR engineers believed in building one machine powerful enough to do the job, rather than coordinating several smaller ones. This was the same thinking that would later produce massive, steam locomotives like the S1 duplex and the Q2. So, the question became, could they build a single electric locomotive powerful enough to replace multiple units? One machine, one crew, unlimited tractive effort for heavy freight service? The FF1 was PRR's answer to that question. The FF1 was designed by Pennsylvania Railroad engineers and built at the railroad's Altoona Works in 1917. It was classified as an experimental locomotive from the beginning. The FF designation indicated a freight electric, with the 1 signifying it was the first of its type. Whether there would ever be a second was very much an open question. The locomotive's most striking feature was its length. The FF1 used 8 driving axles arranged in a continuous rigid frame. Every axle was powered. Every motor was mechanically connected to the others through a system of side rods and crank pins, similar to a steam locomotive. The entire assembly measured over 60 feet in length. This was not an articulated design. There were no pivoting trucks, no flexible joints between sections, no independent motor groups. The entire locomotive was one rigid structure, essentially a massive steel beam riding on 8 fixed axles. This decision, to make Big Liz rigid rather than articulated, was deliberate. In 1917, articulated electric locomotives were largely unproven in the United States. While European railroads had experimented with articulated electrics, American engineers were skeptical. They worried about the complexity of coordinating multiple independent motor groups, the difficulty of distributing electrical power evenly across articulated sections, and the mechanical stresses at articulation points. A rigid frame seemed simpler. It seemed stronger. PRR engineers believed that if they kept the wheelbase rigid and the mechanical connections direct, they could build something more reliable and more powerful than any articulated design. They were correct about the power. The FF1 could pull harder than anything else on rails. but reliability would prove to be another matter entirely. The nickname Big Liz was never official. It came from the operating crews who worked with the locomotive and witnessed its behavior firsthand. Nicknaming unusual or problematic locomotives was common practice on the Pennsylvania Railroad, and Big Liz was certainly unusual. The FF1's wheel arrangement is sometimes described as a 4-8-8-4 equivalent, though that classification doesn't quite capture its unique design. Unlike a typical articulated locomotive with separate engine units, the FF1's 8 driving axles were all part of a single rigid frame. The leading and trailing trucks, each with 4 wheels, were meant to guide the locomotive into and out of curves, but they carried no motors and provided minimal lateral flexibility. The entire weight of the locomotive rested on the driving axles, which were mechanically coupled through side rods just like a steam locomotive. This coupling ensured that all 8 axles turned in perfect synchronization, driven by multiple large electric traction motors mounted in the frame. This mechanical arrangement gave the FF1 extraordinary tractive effort. At low speeds, it could pull trains that would stall any other single locomotive of the era. The electric motors provided maximum torque from a standstill, and the 8 coupled axles distributed that force across the rails without slipping. But this design had severe limitations that became apparent almost immediately. First, the suspension was primitive even by 1917 standards. The driving axles had minimal lateral play, the small amount of side-to-side movement that allows wheels to negotiate imperfections in track alignment. This lack of lateral flexibility meant that even minor irregularities in track geometry transmitted directly into the frame as stress. Second, the rigid wheelbase was extraordinarily long. The distance between the first and last driving axle was far greater than on any successful locomotive before or since. Every inch of that wheelbase had to follow the exact same path through curves and overgrade transitions. On perfectly straight, perfectly level track, this wasn't a problem, but perfect track doesn't exist in the real world. Third, the weight distribution was extreme. Each axle carried an enormous load, far heavier than what PRR's other electric locomotives imposed on the rails. Track that could handle normal traffic began showing accelerated wear after the FF1 passed over it regularly. In terms of pure electrical and mechanical function, the FF1 worked exactly as designed. The motors were reliable, the mechanical connections were robust. The locomotive could generate incredible pulling power and sustain it indefinitely. As a stationary test of electric traction technology, it was a complete success. But locomotives don't operate on test stands. They operate on real track, at real speeds, under real conditions. And that's where the FF1's fundamental problems emerged. The FF1 did not randomly derail itself, despite what some dramatic retellings suggest. The real problem was far more subtle and far more dangerous. Dynamic instability at speed. To understand what happened to Big Liz, you need to understand a phenomenon called hunting oscillation. When a rail vehicle moves forward, its wheel sets don't track perfectly straight. Due to the conical profile of railroad wheels and the relationship between wheel and rail, wheel sets naturally develop a side-to-side oscillation called hunting. The wheel set moves slightly to one side, contacts the rail at a different point, and then rebounds to the other side, creating a sinusoidal path down the track. In a properly designed locomotive, this hunting motion is controlled and damped by the suspension system and the ability of trucks to pivot slightly relative to the frame. The oscillations remain small, and the locomotive rides smoothly. The FF1 had neither effective suspension damping nor pivoting trucks. Its rigid wheelbase meant that instead of individual wheel sets hunting independently and being controlled by flexible truck designs, the entire locomotive body tried to hunt as a single unit. At low speeds, this wasn't catastrophic. The hunting frequency was low, and the forces involved were manageable, but as speed increased, everything changed. The rigid wheelbase of the FF1 meant that small imperfections in track alignment, imperfections that normal locomotives could absorb and negotiate, were amplified into violent lateral forces. A slight misalignment at one end of the 8-axle group would force the frame to twist, transmitting stress to every other axle. Those axles, unable to move independently, would push against the rails, creating lateral loads the track wasn't designed to handle. This wasn't just uncomfortable for the crew, it was damaging to the railroad itself. Sections of track that the FF1 operated over regularly began showing excessive rail wear, particularly on curves and grade transitions. The lateral forces from the locomotive's rigid frame were literally hammering the rails out of alignment. As track geometry degraded, the hunting oscillations got worse, creating a feedback loop. The worse the track became, the more violently the FF1 hunted. The more violently it hunted, the faster the track deteriorated. Crews reported that above moderate speeds, the locomotive developed a pronounced side-to-side motion that became increasingly violent. The ride was rough and unpredictable. At higher speeds, the oscillations could become severe enough to risk derailment, not because the locomotive was mechanically failing, but because the dynamic forces between wheel and rail were exceeding safe limits. The Pennsylvania Railroad imposed strict speed restrictions on the FF1. It could only operate on specific routes with well-maintained track, and even then, only at limited speeds. These restrictions eliminated most of the locomotive's theoretical advantages. A powerful locomotive that can't run fast enough to maintain schedules isn't particularly useful. There were documented incidents of instability, and while the FF1 never suffered a catastrophic derailment that destroyed the locomotive, the risk was real enough that operating crews became reluctant to push it hard. A locomotive that made experienced enginemen nervous was not one the railroad could rely on for daily service. The FF1's operational career was brief and limited. After its completion in 1917, it entered service on electrified portions of the PRR mainline, primarily in the Harrisburg-Paoli region, where the railroad had extended electrification beyond the New York terminal area. But it never became a workhorse locomotive. Instead, it was restricted to specific routes where track conditions were optimal, curves were gentle, and speeds could be kept low. Even on those routes, it was used sparingly. Operating crews developed a reputation for the locomotive quickly. The nickname Big Liz was not affectionate. It reflected the locomotive's size and its tendency to behave unpredictably. Enginemen who had to run it at speed reported an uncomfortable, unsettling ride that only got worse as velocity increased. That kind of reputation spreads quickly among railroaders, and it ensured that the FF1 was never anyone's first choice for an assignment. The Pennsylvania Railroad's response to the locomotive's problems was characteristically understated. There was no public announcement of failure, no dramatic condemnation. The railroad simply stopped using it for regular service. The FF1 became, in effect, a test platform, used occasionally for experimental purposes, but never integrated into the normal locomotive roster. No follow-up units were ever ordered. The FF1 designation suggested there might be an FF2 and FF3, a whole class of these powerful freight electrics. But the Pennsylvania Railroad's engineers had learned enough from the first one. There would be no others. By the early 1920s, the FF1 was effectively retired. It was eventually scrapped, and no effort was made to preserve it. This wasn't an oversight. The Pennsylvania Railroad saw no reason to preserve a failed experiment. The locomotive had taught them valuable lessons, but those lessons were about what not to do. The failure of the FF1 fundamentally changed how the Pennsylvania Railroad approached electric locomotive design. Future PRR electrics favored shorter, rigid wheelbases, articulated designs, and sophisticated suspension systems. The P5 class, introduced in the 1930s, used a much shorter, rigid wheelbase and featured significantly improved suspension. But even the P5 wasn't the final answer. The locomotive that truly succeeded where Big Liz failed was the GG1. Introduced in 1934, the GG1 incorporated every lesson the Pennsylvania Railroad had learned from its earlier electric experiments. It used an articulated design with 2 3-axle trucks that could pivot independently. This allowed the locomotive to negotiate curves smoothly, while distributing weight evenly across 6 driving axles. The suspension system was sophisticated, allowing controlled movement that absorbed track irregularities rather than amplifying them. The GG1 was flexible where the FF1 had been rigid. It could operate smoothly at speeds the FF1 could never safely reach, and it became one of the most successful electric locomotives ever built, remaining in service for nearly 50 years. The contrast between the FF1 and the GG1 illustrates the fundamental lesson the Pennsylvania Railroad learned. Raw power is easy to generate. Controlling that power, integrating it with the track structure, and maintaining stability at speed, that's the real engineering challenge. The FF1 proved that you could build an immensely powerful locomotive, but power without stability is useless. A locomotive that damages its own track, that can't run at practical speeds, that makes experienced crews nervous. That's not a successful machine, no matter how impressive its specifications look on paper. The Pennsylvania Railroad never attempted anything like Big Liz again. The era of ultra-rigid, ultra-long electric locomotives ended with the FF1's quiet withdrawal. Every successful electric locomotive that followed understood that flexibility, not rigidity, was the path to reliable high-speed operation. Big Liz was the most powerful electric locomotive of its time, but it shook itself into obsolescence, and in doing so, taught engineers a lesson that would shape electric locomotive design for generations to come. Power alone doesn't make a good locomotive. Control, stability, and respect for the dynamics of wheel-rail interaction, those are what separate success from failure. The FF1 had all the power it needed. What it lacked was the wisdom to use it safely.